Hello everyone. We will continue our discussion on infrared. I was teaching you that if there are n number of atoms in an organic compound, we have about 3 n minus 6 vibrational energy levels, and a simple compound like methane would have 9 vibrational modes, and benzene would have about 30 possible vibrational bands. So, the vibrations, these vibrations must cause a change in the dipole moment if I have to see an infrared spectrum. So, the molecules containing symmetrical groups may not be infrared active. So, the compounds like ethylene, very symmetrical compound, carbon dioxide is a very symmetrical compound. So, you will not see any infrared spectrum for carbon dioxide. Similarly, for if there are absorption occurs outside the sometimes outside the IR region, sometimes these things do not show peak, sometimes they occur, they are too weak to show up in the infrared spectrum. Such peaks also will not be observed. So, the observed number of absorption peaks are much less than the predicted number. So, but still they are quite large. Further, you will see that additional absorption bands may occur because of the overtones. That is, I had told you that the overtones are peaks at 1.5 to 1/3 wavelengths with greatly reduced intensity of the same IR peaks. Sometimes I get combination bands, that is sum of 2 or more different wave numbers as another peak. Sometimes I get difference bands, difference of 2 or more wave numbers, etc. So, these are additional peaks, and one requires a special eye or special knowledge to interpret these peaks. It is not everybody that they can recognize each and every peak in infrared spectrometry. So, we are going to talk about molecular vibrations in infrared spectroscopy. So, how we essentially visualize an infrared spectroscopy or vibrations. A molecule essentially resembles a set of balls of varying masses. So, this is a very standard way of representation of the compounds or atoms. You must have seen in number of books that hydrogen is represented as one ball and oxygen is represented as another ball, etc. So, you look at the structures of the molecules, we normally represent them as balls of different sizes, because hydrogen has got only one atomic weight and oxygen has got 16. So, the ball of oxygen should be bigger than hydrogen, something like that. So, essentially what we are talking is a functional group or an organic model of an organic compound must be composed of several balls of varying sizes and connected with springs. That is the model. You can buy them in the market, they are available, and that is what I am going to explain to you now. So, a molecule is nothing but a number of balls representing a functional group. So, for methane, what I have is I have one carbon atom at the center, and then I make 4 holes, and then put 3 hydrogen at the bottom like a pyramid, one at the top, that is tetrahedral molecule. So, I can show you some of those pictures. So, I can write a compound like methane, one ball, okay, then one bond here, one bond here, one bond here, this is hydrogen, this is third hydrogen, okay, and there is one more hydrogen at the top. So, this is how we represent. So, each hydrogen is represented as a ball, and these are connected through a line, and instead of line I can represent the whole thing like this. This is my carbon, this is one spring connected to hydrogen atom, and another spring connected to another hydrogen atom, another spring connected to another hydrogen atom, connected to another hydrogen atom. So, this is how this is known as ball model. Similarly, I can write for this is for methane. Now, suppose I want to write benzene or ethylene. So, what is the formula for ethylene? CH2 double bond CH2. I have one carbon here and then one carbon here, one double bond and one hydrogen here, one hydrogen here, okay, and this is hydrogen, this is another hydrogen. So, this I can represent as ball model. One big carbon, okay, and one more big carbon atom, and then a hydrogen atom, second hydrogen, this is third hydrogen, this is fourth hydrogen. So, I can represent another model, another bond like this. This is ethylene. Like that, I can make a ball model for many of these things. I can represent them like this. So, the molecule essentially resembles a system of balls of varying masses corresponding to the atoms of a molecule and springs of varying lengths corresponding to various chemical bonds. So, there are two kinds of vibrational fundamental vibrations. One is known as stretching. So, another is known as bending. Now, you can imagine I am holding two balls here, one like this is one ball and I have one more ball here like this. These two are connected by a bond. I can pull them away, pull them nearer. So, like that, this is known as stretching. Very simple conception, a stretching. And another one is bending like this, or they can bend towards you or they can bend towards me also. So, there are different kinds of stretching and bending operations occur. One can stretch like this, another can bend like this, different ways of bending. So, this you can imagine only if you imagine that they are balls attached with a spring, then only you can do stretching and bending vibrations. That is a simplified model, it is not the actual model. So, the various kinds of stretching and bending vibrations occur at different quantized frequencies. So, when infrared radiation of the same frequency is incident on the molecule. So, you can imagine that the bonds are like this, they are all always stretching. Now, I have infrared radiation falling on this system. So, the stretching vibration, when it is matching, the frequency of the infrared is matching with the stretching frequency, then excitation can occur, excitation to next higher energy level. So, at that time infrared radiation is absorbed and the amplitude of the vibration increases correspondingly depending upon the amount of electromagnetic radiation, that is IR, absorbed. So, when the molecule reverts to the ground state, the absorbed energy is lost. This I have explained to you earlier, that the absorbed energy is sometimes lost to other molecules or as heat or in some other fashion, usually by collision with other molecules present in the same sample or matrix components. Okay. Quite often the molecule reverts to the ground state where the absorbed energy is released as heat. Heat also is quite possible. So, what are the different kinds of vibrations that can occur in a given system? Look at this slide now. So, here I am representing a ball model. I am also showing you the stretching types. So, here I am showing you the stretching vibration. Here is my central ball, you can imagine this is CHO, okay. You can imagine, or CH2. Here it can be a carbon atom and this can be a hydrogen atom and this can be another hydrogen atom. So, the two hydrogen atoms are connected to the carbon atom and this is the axis, that is the compound axis, organic compound axis, how we imagine the compound. This is only a functional group, that means it is only a part of the organic compound. Okay. So, now I have look at these two figures carefully. You can see that the bond between this one and this one is stretching towards top and this is also stretching towards the top. That means both of them are getting pulled simultaneously like this, like this. So, the stretching takes place in the same direction simultaneously, but look at the other picture now. Here what is happening? The central ball is here and hydrogen is here, another hydrogen is here. When this is stretching, this is contracting. So, imagine when this is stretching, this is contracting like this. So, a dynamic picture of a stretching frequency can be both of them simultaneously going up and up, so up and down, up and down, up and down, or this goes up, this comes down, this goes up, this comes down like this. This is known as asymmetric stretching. Okay. So, there are two kinds of infrared peaks we will get. If the stretching is symmetrical, I get a one peak, and if the stretching is asymmetrical, I get another peak. Obviously, the energy required for this kind of transition is different, isn't it? So, I will get two peaks. So, good organic chemists can recognize a stretching frequency. Among the stretching frequency, one can recognize a symmetrical stretching and another is asymmetrical stretching. A symmetrical stretching will occur at it requires less energy, whereas asymmetric stretching will require more energy. So, less energy, the peak at less energy would be appearing at longer wavelength and the peak at more energy, the peak corresponding to more energy transition would appear at the shorter wavelength. So, these are the molecular vibrations involving stretching. Okay. Now, look at the molecular vibrations of another kind. I had explained to you earlier that the vibrations can occur in stretching and bending. Now, I am going to show you the bending vibrations. So, how do these bending vibrations appear? You look at the slide now. Here I am showing two types of vibration. Okay. Here as usual my central atom is here, axis is here, two hydrogen bonds or two balls are here. Now, imagine I have a carbon atom here like this. Okay. Now, both of them are going like this, both of them are coming like this. Okay. This is known as rocking. They are in plane, in the same plane, isn't it? The axis is at the bottom and they are like this. In the same plane, I am pushing them this side and then I am taking them back this side. This is known as rocking. So, even in rocking, I have different another possibility that when one is coming this side, other may also be moving away from it relatively or coming towards it relatively. Now, I can show you that very simply like this. This is known as scissoring. Just imagine like this. Suppose I increase it more, does it not look like a scissor? My hands. Okay. Now, the other one is rocking like this. So, rocking and scissoring are in plane bending. That means, they occur in the same plane. Now, I will show you out of plane deformation. This is molecular vibration bending, same title. I have the two types again, central ball, axis and two more hydrogen atoms, and similarly another one, and here you can see that I have put plus sign here and one plus and one minus sign here. Now, look at my hands now. Earlier I had shown you like this. Now, I am showing you this is out of plane. Imagine my screen, imagine my screen as one plane. I am going behind the screen and coming towards you. So, the balls are moving like this. Now, if I put plus sign, that means both of them are coming towards you and going back simultaneously. Okay. Both of them are going back or coming towards you. Now, when I put one plus and one minus, it will be like this. The molecular vibrations would be appearing like this. So, this will be, this is known as twisting, and this is wagging, tank, 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 like that. There are different kinds of vibrations that appear. These are out of plane deformations. So, just to make sure that you have understood, I am going to show them once again to you. Okay. So, this is symmetrical stretching, both of them are stretching away from each other, and in this case asymmetrical, they are stretching one away, one towards this thing. And then I have 4 bending vibrations, 2 of them are in plane, they are known as rocking, another one is scissoring, and the next one is wagging, and twisting. Okay. So, these are the different kinds of vibrations generally occurring in infrared spectroscopy. So, how do I go looking that for which bending, which rocking, which is twisting the etc., what kind of wavelengths or what kind of transitions can occur. Now, how do I recognize all these things? Means people have studied different compounds and made a table of where such peaks appear, and then what they find out is bending vibrations you generally require less energy. You see, bending vibration just a little bit, but stretching requires more energy. So, the stretching frequencies must appear at longer wavelength or shorter wavelength. The stretching frequencies must appear at shorter wavelengths, that is higher centimeters inverse, between 4000, 5000, not 5000, 4000, 3000, 2000 like that, and bending vibration should occur towards the other end of the spectrum. Okay. Now, stretching vibrations are also found to occur in the order of their bond strength. Okay. So, the bond strengths are also important. So, the bond strengths are also important. Now, you will remember that what I have taught you about single bonds, double bonds, etc. Now, if you remember the chemistry correctly, you know that single bonds are sigma bonds, double bonds are pi bonds, and then there are acetylenic bonds with 2 pi bonds. Okay. So, then there are atoms or functional groups with non-bonded electrons also. Okay. Now, what I have been saying? I have been saying that the stretching and bending vibrations represent the bond strengths. So, suppose I have a single bond, a double bond and a triple bond. Which one would be having maximum bond strength? Just I am giving you 2 seconds or 3 seconds pause, you can think of it. Which one, single bond, double bond and triple bond, which one would be having higher strength? Okay. Now, I have having 3 seconds are over. I want to tell you that single bond is less strong than double bond. Double bond is is more stronger than double bond is less strong than triple bond. So, among the 3, triple bond is very strong and double bond is less than that and single bond is still less than that. So, a triple bond would be the bond length in a triple bond would be very small compared to a double bond, and that is very small compared to a single bond. Single bond would be having larger bond length. So, larger bond length means the energy corresponding to that would be less. Now, we will come back to this slide now. Now, look at this slide. Here I have carbon carbon triple bond and carbon carbon double bond. Okay. So, in this carbon carbon triple bond, where do I have the infrared peak? The infrared peak for triple bond is somewhere between 2300 to 2000 centimeters inverse. Corresponding micrometers is 4.42, it should be 5.0, 4.4 to 5 microns. I will correct that. Okay. So, it should be 5.0 microns. So, carbon carbon all double bonds and all triple bonds in a given inorganic compounds, if you take their IR spectrum, the IR peak should appear between 2000 and 2300 centimeters inverse. This is what we are talking about, the appearance of the peaks. A double bond or a triple bond should appear at the lower wavelength range. Now, look at the next same slide, another concept. Here I have three triple bonds, three compounds. One is carbon carbon single bond, one is carbon nitrogen single bond, and another is carbon oxygen single bond. Now, carbon is common here, okay, and here it is carbon, it is nitrogen, it is oxygen. What is the atomic weight of carbon? Is 12, nitrogen is 14 and oxygen is 16. So, when I have this, the peaks will appear between 1900 to 1500 centimeters inverse, and there is one more peak appearing somewhere around 1300 to 800 centimeters inverse. Okay. Now, look at this, corresponding numbers are microns, okay, micrometers, 5.3 to 6.7 and 7.7 to 12.5. Now, compare this double bond position with respect to single bond position. So, obviously, like our earlier theory of single bond is longer, it is having less energy compared to double bond. So, single bond should appear at longer wavelength, right. So, here it is appearing at 1500 compared to 2000 of a double bond. Again we go back to this slide. So, this is what it represents. Okay. So, single bond 1900 to 1500 and carbon carbon, you can see this here, carbon carbon single bond, this is carbon carbon double bond. So, single bond is 1900, carbon carbon double bond is 2300 to 2000. Now, look at another combination. Here I have put NH, CH and OH. Now, hydrogen atom is common in this side, okay, and it is a single bond, and the atomic weight of nitrogen is again 14, this is 12, this is 16. Now, all these single bonds containing hydrogen atom in the functional group appear between 3700 to 2630 centimeters inverse. Okay. So, the range is important in this case, but not the numbers. Okay. See the numbers what I am giving you in this infrared spectrum, they are all approximate. For every compound with the same functional group, it will show you the peak at the same point, but another compound with the same functional group will show you at a peak at the same point, but differing slightly depending upon the molecular structure. Okay. For example, COOH group shows a peak around 1640 centimeters inverse. All carboxylic acids will show you a peak around 1640, but not exactly at 1640, because the molecular size will be different, molecular weight will be different, and the environment will be different like that, but there it will be around that 1640 centimeters inverse like that. In this case, look at the slide now, carbon carbon, carbon nitrogen, carbon oxygen, they all appear around 1900 to 1500. That is why the range is also slightly bigger. Now, in the same way I can take a look at NH, CH and OH group, that is that appears around 3700 to 2630, even though it appears exactly same way in the same compound, but if the molecular weights are different and molecular structure is different, they appear in the same range, but at different places. That is what you should understand. Now, compare this with another IR characteristic. Here I have taken oxygen and it is deuterium. Okay. Molecular weight of deuterium is twice that of hydrogen. So, oxygen hydrogen and oxygen deuterium. So, where is the peak? Oxygen deuterium is occurring at 2630 centimeters inverse, okay, and that is around 13.8 microns, and oxygen hydrogen, this is something like alcohol, okay, OH group. So, an alcoholic group appears at 3570 centimeters inverse. So, what I am trying to tell you here is, if you know the structure of a compound and one of them is deuterated, then you will see two peaks for the deuterated compound as well as undeuteriated compound. So, OD and OH appear differently. So, that is important as far as our studies are concerned. So, again coming back to the top portion of this slide, bending vibrations generally requires less energy, that is understood. So, they occur at longer wavelengths, that is understood, than the stretching vibrations, and stretching vibrations are also found to occur in the order of their bond strength. So, I have here a change for carbon carbon double bond, carbon carbon triple bond and carbon carbon single bond. Among the three, these are bending vibrations. You can see carbon carbon single bond, carbon nitrogen, carbon oxygen, lower wavelengths. Similarly, different wavelengths for different compounds, and OD, OH different compounds. Like that, infrared spectroscopy can be used to interpret different IR peaks for different compounds. Okay. Now, an approximate value of the stretching frequency of a bond can be calculated. This is a little bit theoretical. We are not going more into the details, but what I want to tell you is, you can calculate the where an IR peak occurs in a given system. So, the quantum mechanical calculations permit us to, even if I without taking the spectrum, I can determine where I can expect an IR peak. So, that relation is given by mu is frequency, mu is equal to 1 over 2 pi c into square root of k divided by mx my divided by mx plus my. This quantity mx my and mx plus my, this you should remember as far as infrared spectroscopy is concerned, because this is here you can see that k is a force constant, that is approximately 5, 10, 15 into 10 raised to 5 dynes per centimeter. For single bond it is 5 into 10 raised to 5, for double bond it is 10 into 10 raised to 5, and triple bond it is 15 into 10 raised to 5, and that is k. Pi, you know, c is velocity of light, mu is the frequency, and mx and my are the masses of the atoms in grams, that is basically atomic weight. Okay. So, If it is carbon, it is 12. If it is hydrogen, it is 1. Oxygen is 16, like that. So, the quantity mx my divided by mx plus my is known as reduced mass. So, this is important. We should know what is reduced mass, and if I know the atomic weights and if I know the force constants, I can predict where I get the infrared spectrum or infrared peak. So, with this much information, we will continue our discussion about the instrumentation. There are many other aspects of instrumentation and sample handling, etc., that we will study in the next coming classes. So, thank you very much.